Okay. These are our exponential functions. You might see them written like this, or you might see them written like this. Basically, when it's written like this whole part is the same thing as the b that's right here. Okay? The a part is going to be our initial amount, or what we're starting with. Okay? The b part's going to be like our rate. Okay, it's our constant ratio. Okay, when we have it written in this form, the 1 plus r is going to be for a growth, and a 1 minus r is going to be for a decay, and the r is our rate. Okay, notice how x is in the exponent. Okay, when x is in the exponent, that tells us it's exponential. Okay, the number of bacteria in a petri dish triples every hour, and there were 6 bacteria in the dish at noon. Use the table below to determine the number of bacteria in the dish for the first 5 hours. So when we set something like this up, the amount we're starting with is the 6. It's telling us it triples, so that's our b value. And then we're going to have the x as the exponent. So the x is going to represent our hours. So if we plug in 0 to this function, 3 to the 0, so it's going to be 6 times 3 to the 0. Anything to the 0 power is 1, so it's just 6 times 1. That's where the 6 came from. Here we're going to plug in a 1. So it's going to become 6 times 3, which gives us 18. And then we're going to plug in a 2. So that's going to give us 6 times 9, which is 54. And then we're going to plug in a 3. So it's going to be 6 times 27. So that's 162. And then we're going to have 6 times 3 to the 4th. 3 to the 4th is 81. So we're going to have 6 times 81. And then we're going to have 3 to the 5th. So 6 times 243 is 1458. Okay, does this represent exponential growth or decay? Well, are my numbers getting bigger or are they getting smaller? They're getting bigger, so this is going to be a growth. So it says, what equation can be written to model the number of bacteria Y in the dish H hours? So this is what we started with. We're going to say Y is, and we're just going to replace the X with an H because they're telling us to use the H for what we're plugging in. So now it says how many bacteria will be in the dish in 10 hours. So we have to do 3 to the 10th. And multiply by 6. All right, example 2. After treatment, a population of insects has 1/4 the number of insects as the prior day. The initial population, so initial is what I'm starting with. Use the table below to determine the number of insects in the population of the first 5 days. So the 1/4 is telling us our B value. I'm going to go ahead and write that down here. So I started with 500,000. And then I'm going to have 1/4 to the X. Okay, so for this problem, we would be plugging in 0, which again is just going to give us a 1 for this part. So that's why we have the 500,000 here. So now we're going to have, there's not really enough space to write in this tiny box. So 500,000 times 1/4. And we're going to get 125,000. And then we're going to raise it to the second. So I'm just going to keep typing it in my calculator. I'm not going to write my work out. So I'm going to take 1/4 and I'm going to raise it to the second power. And then I'm going to multiply that by 500,000. And then here I'm going to take 1/4, raise it to the third power. And multiply by 500,000. And then I get 7812.5. And then same thing. And 1953.125. And then 488.28. Okay, so does the scenario represent growth or decay? It's getting smaller every time, so it's going to be a decay. What will the population be in 7 days? So if I take my original equation and I have 1/4 to the 7th, I'm going to do 1/4 to the 7th and multiply times 500,000. And it runs to about 30. Okay. All right, next example.